Today, we're going to study algebraic field extensions in more detail. We begin with the following theorem. Let E be an algebraic field extension of the field F. And let sigma be an embedding of F into L, where L is an algebraically closed field. Then sigma extends to an embedding sigma hat of E into L. So the diagram here is like this. So F is embedded into E and is mapped to L, where this extension is algebraic and this embedding is sigma. Then there exists an embedding sigma hat such that sigma hat restricted to F is equal to sigma. Furthermore, if E is algebraically closed and L is algebraic over its subfield sigma of F, then sigma hat is an isomorphism. Let's give a proof of this theorem. Consider the following set of pairs. So these are pairs K and tau, where K is a field extension which is in between F and E, and tau is a map from K to L such that tau restricted to F is equal to sigma. We introduce a partial order on the set A in the following way. So we say that K1 tau 1 is less or equal to K2 tau 2 if, first of all, K1 is a subfield inside K2, and secondly, tau 2 restricted to K1 is equal to tau 1. What we see is that this set A satisfies the conditions of Zorn's lemma. Indeed, for Zorn's lemma, we require that every chain has an upper bound. And so if we have a chain K1 tau 1 less or equal to K2 tau 2 less or equal to K3 tau 3, and so on, then we can set K to be the union over J from 1 to infinity of Kj. And since all these maps taus are compatible in this way, so then these maps also glue in a single map tau. So we get upper bound K tau. And now by Zorn's lemma, this set A has a maximal element. So which will be a pair M and mu, where M is a field between F and E, and mu is an embedding of M into L. We claim that M, in fact, must be equal to E. We prove this by contradiction. Suppose we have alpha in E, which does not belong to M. We have that alpha is algebraic over M. Since it's algebraic over a smaller field F, then this tells us that there exists F irreducible in M of x such that f of alpha is equal to 0. Then we know that the field extension M of alpha is isomorphic to M of x, quotient by the ideal generated by F. The map mu is an isomorphism between M and sigma of M, which is inside L. And consider mu of F. This will be a polynomial with coefficients in mu of M. Since mu is an isomorphism, so this mu of F is irreducible. Our assumption that L is algebraically closed and mu of F may be viewed as a polynomial with coefficients in L. Then we conclude that there exists a root beta in L of polynomial mu of F. So mu of F evaluated at beta is equal to 0. So this tells us that if we take mu of M and adjoin to it the root beta, then the resulting field is isomorphic to mu of M of x, quotient by ideal generated by mu of F. The fields in the right-hand sides of these isomorphisms are isomorphic by the map mu. So this tells us that the fields in the left-hand sides are also isomorphic. So this tells us that M of alpha is isomorphic to mu of M with a joint beta. And the isomorphism that sends one to another will send alpha into beta. This tells us that the pair M of alpha and mu hat is an element of A. And this gives us a contradiction to our assumption that the pair M mu was a maximal element. The source of this contradiction is our assumption that M is not equal to E. Hence, in this maximal element, M is equal to E, and the map mu is the map sigma hat that we seek. This completes the proof of the first part of the theorem. For our second claim, if E is algebraically closed and L is algebraic over F, then this implies that L is algebraic over sigma hat of E, and sigma hat of E is algebraically closed itself. Since L is algebraic, every element of L is a root of some irreducible polynomial with coefficients in sigma hat of E. But sigma hat of E is algebraically closed. So each root of such a polynomial will be already there. So this tells us that L must be equal to sigma hat of E. And this means that sigma hat is an isomorphism. As an immediate corollary, we get that any two algebraic closures of a field F are isomorphic. So which means that essentially up to an isomorphism, the algebraic closure of a field is unique. Now let us consider the following situation. So suppose we have a field F which is contained in an algebraically closed field L. And let element alpha in L be algebraic over F. So let polynomial F be the irreducible polynomial that has alpha as a root and with coefficients in F. Then we know that if we adjoin alpha to F, then the result is isomorphic to the quotient of the ring of polynomials by the ideal generated by F. Now let us denote this field extension by E. So E is F of alpha. We consider the maps sigma from E to L such that sigma restricted to F is identity. The sigma has the property that it acts identically on elements of F, but it is allowed to move alpha around. Our claim is that the number of such embeddings sigma of E into L is equal to the number of distinct roots of this polynomial F in the field L. Indeed, let beta 1 through beta k be roots of F in L. Since F is irreducible, so this tells us that the extension of F with each root beta j is isomorphic to F of x quotient by the ideal generated by polynomial F, which is isomorphic to F of alpha, because alpha is one of these roots. This isomorphism gives us the maps sigma j that will send F of alpha isomorphically to F of beta j. So for each of these roots, we have the map sigma j, which acts from E to the field L. And of course, each of these maps sigma j's will fix elements of F. Now let us show that these maps sigma j exhaust all possible embeddings. Suppose sigma sends E to L, and sigma restricted to F is identity. We want to show that sigma of alpha is one of the roots beta 1, beta k. Now we have F of alpha is equal to 0, since alpha is a root of the polynomial F. So this tells us that sigma of F of alpha is still equal to 0. But sigma acts identically on elements of F, and the coefficients of this polynomial are in our field. So this tells us that sigma of F of alpha is the same thing as F of sigma of alpha. And this is equal to 0. And this tells us that sigma of alpha is a root of the polynomial f, and so this tells us that sigma of alpha belongs to the set beta 1 through beta k. With this proposition, we are getting closer to Galois theory. Now we have learned how to count the number of embeddings of this kind. And we saw that the number of such embeddings is given by the number of roots of the irreducible polynomial that defines this extension. Let f be a polynomial with coefficients in the field f. Definition. An extension E of the field f is called the splitting field of little f if there exist roots alpha 1 through alpha n in the field E, such that f of x factors as a leading coefficient times x minus alpha 1 ... x minus alpha n, and the field E is generated as a field extension over f by these roots. Now let's look at an example. Suppose as our base field we take the field of rational numbers, and as a polynomial f of x, let's take x cubed minus 2. This polynomial is irreducible in Q of x, and it has the following roots. It has one real root, cube root of 2, and it has complex roots that are cube root of 2 times e to the 2 pi I over 3 and cube root of 2 times e to the 4 pi I over 3. Then we see that the splitting field of this polynomial of x cubed minus 2 is the following extension of rational numbers. So we add cube root of 2, and we add these two complex roots as well. So cube root of 2 times e to the 2 pi I over 3 and cube root of 2 times e to the 4 pi I over 3. But this can be simplified. So here we add cube root of 2, but then we see that if we add this pair, cube root of 2 and cube root of 2 times this third root of unity, then the third root of unity will also be in this field extension. So this means that we can just add e to the 2 pi I over 3, which is a complex root of 1 of degree 3. And we see that the splitting field has these two generators. Once we add this root of unity, then the second one will be automatically adjoined because the second one is just the square of the first one. Our next proposition states that the splitting field is also unique up to isomorphism. So we have proposition. Let E1 and E2 be two splitting fields of a polynomial f in f of x. Then there exists an isomorphism tau from E1 to E2 such that tau restricted to the field f is identity. Let's give a proof. Let f bar be the algebraic closure of the field f by the theorem on field embeddings that we proved at the beginning of this class. There exists an embedding sigma 1 of E1 into F bar, and the embedding of E2 into F bar. So the diagram here is like this. So F is contained in E1 and E2, and here we embed both of them into F bar. So this will be sigma 1 and this is sigma 2. Since E1 and E2 are splitting fields, both sigma 1 of E1 and sigma 2 of E2 are generated by the roots of the polynomial f in the algebraic closure. Hence, we conclude that these two fields coincide. The image of E1 in F bar must be equal to the image of E2 in F bar. And this tells us that these two fields are isomorphic, and the isomorphism tau is sigma 2 inverse times sigma 1, which completes the proof of this proposition. So this proposition tells us that the splitting field of a polynomial is uniquely determined by that polynomial. Now we state the main result of this lecture. Theorem. Let E be the following field extension of F that sits in the algebraic closure of F. The following conditions are equivalent. 1. Every embedding sigma of E into F bar over F, so this means that sigma restricted to F is identity, is an automorphism of E. So it doesn't mean that sigma is identity on E, but it means that sigma of E is equal to E. 2. E is a splitting field of a family of polynomials in f of x. Well, previously we defined the splitting field of a single polynomial, but in the same way it's clear how to define the splitting field of a family of polynomials. And 3, if an irreducible polynomial f in f of x has a root in E, then f factors into linear factors over E. So this means that all roots of f belong to this field E. Clearly, not every field extension satisfies these conditions. What this theorem says is that these three conditions are equivalent. So if a field extension satisfies one of them, then it satisfies them all. This motivates the following definition. An algebraic field extension E of the field F that satisfies the conditions of this theorem is called normal extension. And let us look at the following example. So let's consider the following extension of rational numbers. Let's take q and add cube root of 2. So here we see that this extension e contains a root of an irreducible polynomial x cubed minus 2, but it does not contain all roots of this polynomial. Because we see that this field is contained in the field of real numbers, and this polynomial has complex roots. So the conclusion is that this field extension does not satisfy the conditions of this theorem, and so this field extension is not normal. Let us prove that 1 implies 2. So we're assuming the property 1, that every such embedding of E into F bar is an automorphism of E. And we want to show that E is a splitting field of a family of polynomials. Well, what is this family? So we consider the family of the following polynomials. So here F is an irreducible polynomial in f of x with a root in E. And we consider all such irreducible polynomials. Suppose alpha in E be a root of such irreducible polynomial f. We need to show that any other root beta in f bar of the polynomial f belongs to E. Since polynomial f is irreducible, we know that the field extension f of alpha is isomorphic to the field extension f of beta. So we have an isomorphism sigma that maps alpha into beta and is identity on the field f. By our theorem on extensions of field embeddings, we get the map sigma hat of E into f bar such that sigma hat of alpha is still equal to beta. But by our assumption 1, sigma hat of E must be equal to E. And this implies that the image of any element of E is still in E, and so we conclude that beta belongs to E. So what we proved is that if we have a root alpha in E of some irreducible polynomial, then all other roots of the same polynomial will still belong to E. And this, in fact, proves 2, and also it proves 3. So here we see that if we take an irreducible polynomial f, which has a root alpha in our field extension E, then f may be factored into linear factors over f bar, because f bar is algebraically closed. And then we prove that all roots of f will actually be in E. And so this means that this irreducible polynomial will factor into linear factors over E as well. So this shows that 1 implies both 2 and 3. Let us now prove that 2 implies 1. Consider the family of irreducible polynomials that E is splitting. And let sigma be the embedding of E into F bar. What we saw is that sigma permutes the roots of each of these polynomials. And E is generated by these roots. This implies that sigma of E is equal to E, and this establishes property 1. Finally, let us prove that 3 implies 1. We assume that 3 holds, and we need to prove that every embedding sigma of E into F bar will keep E invariant. So that is, we need to show that for every alpha in E, sigma of alpha is again in E. Since our extension E is algebraic, so here we can say that alpha is algebraic over F. And this tells us that alpha is a root of irreducible polynomial f in f of x. By property 3, we know that every irreducible polynomial that has one root in E actually has all roots in E. So this means that f of x will factor as an times x minus beta 1 times ... x minus beta n, where the roots beta j are in E, and alpha is one of these roots. We saw that sigma permutes the roots beta 1 through beta n. And this tells us that sigma of alpha is still in the same set, beta 1 through beta n, and this is a subset inside E. So this tells us that sigma of alpha is in the field E. And this shows that this field extension E is invariant under sigma. This proves that 3 implies 1 and completes the proof of this theorem. In conclusion, let's make the following remark: that every extension of degree 2 is normal. So that is, so if we have E an extension of f and the degree of E over f is equal to 2, then E is normal over f. Now, what does this mean? So this means that dimension of E as a vector space over f is equal to 2. So let alpha be an element of E which is not in f. Then the set 1, alpha, and alpha squared is linearly dependent over f. And this tells us that if we consider an irreducible polynomial of alpha with coefficients in f, then this tells us the degree of this polynomial is equal to 2. And since alpha is a root of f, so this tells us that f of x is divisible by x minus alpha. But then, so this tells us that f of x will simply factor as x minus alpha times x minus beta, where x minus beta is the result of division of f of x by x minus alpha. And this division is carried out in E of x. And this tells us that the second root, beta, must also be in E. And this tells us that this field extension E is a splitting field of this polynomial f of x. And here we see that the fact that degree of this extension is equal to 2 plays a crucial role. Because if the degree were higher, then instead of getting a linear factor, we will get a factor of a higher degree, and there would be no guarantee that it splits into linear factors over E. Let us present an example. Consider the following chain of field extensions. So let us take the field of rational numbers. Then we take its extension with the square root of 2, and the extension of that with the fourth root of 2. So the first extension is of degree 2, and thus normal. And the second extension is also of degree 2, and by the previous remark, it's also normal. However, the total extension, so Q to adjoining fourth root of 2, is not normal. To see this, we observe that the irreducible polynomial of fourth root of 2 is x to the power of 4 minus 2. This is irreducible in Q of x, say by Eisenstein's criterion. But the roots of this irreducible polynomial are plus minus fourth root of 2 and plus minus fourth root of 2 times I. And we see that not all roots of this irreducible polynomial belong to this extension, since this extension is purely real. The conclusion: here we have an irreducible polynomial that has one root in this field extension, but not all roots are in this field extension, and thus this field extension is not normal. This example shows us that we have to be careful with normal field extensions. We could have a chain of field extensions where each step is normal, but the overall field extension is not normal.